So first I would like to thank the organizer for giving me this opportunity. I'm speaking about automatic numbers. Automatic numbers and a method called Mahler's method, which has to do with transcendence and algebraic independence of complex number. So the starting point, I'm going to explain what automatic numbers are. And first, the talk is related to base B expansion, so integer-based expansion of real numbers. And such expansion provide a natural way to a natural correspondence between numbers and sequences of a finite alphabet. And you can use this correspondence to try to classify numbers in different ways. So this can be done using, say, dynamical systems or probability, or also using computational complexity. So in this talk, I will focus on the third aspect. And I start by recalling, before introducing automatic numbers, recalling what computable numbers are. So, computable numbers. So there are various ways to define them, but roughly it means that a number is computable if there exists a Turing machine that produces its, say, base B expansion for some integer base B is equal to 2. And so there are quite different kind of Turing machine and way you can use a Turing machine. So I want to be a little bit more precise. In this definition, you can choose a Turing machine that you use as transducers. So it means that you will have something like this. So the machine has a finite control, which corresponds to the physical states of the machine. And you have some, say, input tape here, and you separate this with an output tape. Here, and here you have some working. So I choose a multi-tape Turing machines. And here you have some, say, working or memory tapes. And then you can say that a number is computable if you feed, so if you start with, say, the base, let's say base K expansion of n as input. So you write the base K expansion of n in the input tape. Then the machine produces on the output tape the nth digit, say, in base B. Okay, so if there exists such machine, you feed the machine with integer, say, K, integer expansion in base K, and it will produce some output, maybe, that correspond to an expansion in some other bases, say, B. So you just have to be careful that there are possibly two different bases, one for the input and one is related to the output tape, so in the way we want to see the number. Okay, and if you consider this model, then it's quite natural to see how automatic numbers arrive. Automatic numbers. So they are defined exactly in the same way, but with much more restrictive models in which you just remove the working tapes. So you remove the memory part of the machine, so which means that all the memory you have is in the finite control, which is actually a finite automaton. And so the memory, say, in some sense, is strictly finite. So it's the same, but without memory tape. And if the expansion on the input is given in base k, we speak about k automatic numbers in base B. So they are written in base B. Again, there are two different bases. Okay, and so the picture we have is like this. So we have here the computable number. Yeah, it's just coming in a few seconds. So I just put this general picture and then I will give you an example. So computable numbers are here, and outside there are the number we don't want to speak about, which are uncomputable numbers. So I'm not really interested into that numbers today. And at the very bottom, so as I said, we classify number with respect to sequences. So at the very bottom, we have periodic sequences. So I just call periodic number, but you understand what it means, which are just the rational numbers. And then the automatic numbers are somewhere here. And before giving some problems related to the numbers, I'm going to give one example. So the usual example is a two-Morse sequence and the two-Morse automaton, but today I will just give a slight variation of it. So we start with a two-state automaton, so which means that this finite control, it can be represented by a finite state machine. So it's a finite graph. It means that we have finite number of states, say in that case 2, A and B. One of the states is special, so it's the initial state, which is marked like this. And then the machine can read, has the ability to read input in some base. So in this example, so K is equal to 3. So the input base is the ternary base. So if you are in the state A and you read either a 0 or a 1, you remain in state A. If you are in state B and you read a 0 or a 1, you stay in state B. And when you read a 2, then you move from one state to the other. So here we have a deterministic finite automaton, which is able to read a ternary expansion of numbers, one digit by one. We choose the convention that digits are read from left to right, but this is if you prefer to read from right to left, then there always exists another machine that is able to do that. And then we have an output function which corresponds to what will be written on the output tape after the reading. So if you are in A, you will have a 0, and if you are in B, you will have a 1. So this machine will produce a sequence that starts like this 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, and so on. So you get binary strings that you can maybe want to see as a binary number, okay? So we have something like psi, which correspond to, so maybe in my notation, I put the dot here. So it corresponds to a real number in 0, 1, which is a 3 automatic number written in base 2, right? I could also consider the same number as written in base 10, and in that case, it's a very different number, okay? So if you think a bit about what the machine is doing, so, and if I call an the nth term of the sequence, so it means an is what you get if you write n in base 3. So you obtain this. So an is equal to 1 if the expansion of n in base 3 has an odd number of 2's and 0 otherwise. So this can be easily checked with the machine. So this is exactly what it is doing. And so it's conference about uniform distribution. And so in this topic, uniform distributions come naturally with the notion of normal numbers. So in that example, so this numbers is simply normal in base 2. But it's not really hard to see that it's not normal in base 2. It's actually quite far from being normal. Well, I think that's it with this example. And the kind of problem we have with these automatic numbers are the following one. So there are two main directions. So the first one, let's call it conjecture 1, is to prove that the classical mathematical constant, classical numbers mathematicians used to work with, except for the rational number. So rational numbers have periodic expansion in all bases, so they are automatic in all bases. But otherwise, you expect that the classical mathematical constants are not automatic. So we can, for instance, conjecture that square root of 2 pi log 2 theta of 3 are not automatic. So when I say are not automatic, so it means they are not k-automatic in any base. So it means for all base B and all k, they are not k-automatic in base B. And this is only known, so far, only known for algebraic irrational numbers. So this was first proved in a joint work with Jan Bujold by using some techniques of Diophantine analysis called the Schmidt subspace theorem, which is a generalization of Roth's theorem. And now there is also a second proof of this that comes from work of Patrice Philippon and joint work myself and Colin Favergent. And essentially all I'm going to speak about today correspond to a joint work with Favergent. Yeah? The input type here. So on the input, yeah, you're right. I'm bit lazy on this. So say on the input tape, you will have a special symbol, and then you write, say, n in base k. So you have some digits here, A1, A2, and so on. And the machine is reading from left to right, and it's online, or also you can say one way. So once you read one digit, you cannot come back to read it again. So it's irrevocable. So it's just you go from left to right and one digit by one. That's a good question. Yeah, if you want to remember something about the first digits here in the expansion, you have to put it on the memory somewhere or on the state here. But you can know more than this. Okay? So this is the first main conjecture. And the second problem is quite different. It's related to, so what we expect is that no classical mathematical constants can be automatic, but still some automatic numbers do exist, like this one. And the point is that if you take this number, for instance, it's written in base 2, and now you move it in base 3, so you consider the same numbers written in base 3, so the digits looks like quite unpredictable. So here, you can easily see that there is a lot of structure into this sequence, but if you move to base 3, everything seems to be broken. Okay? So, and we would like to have some formal explanation for that. So one first conjecture is that if alpha is a real number such that if alpha is, say, automatic in base B1 and B2, so in two different bases that we assume to be multiplicatively independent, so log B1 over log B2 is not a rational number, then alpha should be a rational number. So which means that if you don't start with, so you start with an automatic number which is not rational, so the sequence is not periodic. If you move to a very different base, then you cannot be automatic anymore. So the structure, the strong structure here, you lose it, you have to lose it. And of course, if B1 and B2 does not satisfy this assumption, so if they are multiplicatively dependent, so if you are automatic in base B1, you are still automatic in base B2. So it's easily seen to be property remains. And actually, I'm interested in a stronger version of this conjecture 2. So conjecture 2 seems to be, say, too hard to be solved at this point. So we try to generalize it to have even something harder. Sometimes it's easier to fight against something harder. And the third conjecture is that now if you pick, if alpha 1, alpha r are real numbers, such that alpha I is automatic in base, say, Bi, and alpha I is not rational, so this for every I, then alpha 1, alpha here should be algebraically, okay, I missed one assumption. So the base B1, Br are multiplicatively independent. Which means that some equation like B1A1, bn an equal 1 in integers implies a1 equal an equals 0. So if the bases are multiplicatively independent, you expect that alpha 1, alpha r are algebraically independent over Q bar. So Q bar means the field of algebraic numbers. So this one says that the same number, so if you consider, say, a number automatic in base 2 and in base 3, they cannot agree, they cannot be the same. And here it says that they are completely different, so they in some algebraic way, so they have to be algebraically independent. So of course, conjecture 3 is much stronger than conjecture 2. Okay, so that's the main problems we have about automatic numbers. And now, yeah, maybe I can keep this. Okay. I want to explain how we can try to attack this kind of question. So if we look at this particular example, so it's easy to see that we have the following relation. So if you consider A of 3n, so which means that if you consider the ternary expansion of 3n, so it's the same as the ternary expansion of n, where you shift and add a 0. Okay, so it's just an, because it has nothing to do with the number of 2's. You just add 1, 0. And the same is true for A of 3n plus 1, because you shift and add a 1, so you get still an. And now if you consider A of 3n plus 2, so if you have an odd numbers of 2, it becomes even. If you have an even, it becomes odd, so you get 1 minus an. So you easily have this relation. And now we are interested in the generating function f of z, which is defined as the sum of a and z to the n. So the generating function associated with this automatic sequence. And we are going to use this to show that this function satisfies a particular kind of functional equation. So what we get is that f of z, so we can split into 3 parts according to the residue class mod 3. So we get f of z is the sum of a of 3n, z 3n, plus the sum of a of 3n plus 1, z 3n plus 1, plus the sum of a of 3n plus 2, z 3n plus 2. And this, according to that, give you, here you get just an, so it's just f of z3 plus z times f of z3 plus z squared over 1 minus z3, because of the 1 where you get a geometric sequence, minus z2 f of z3. Right? So it gives you an equation which is z squared 1 minus z3 minus f of z plus 1 plus z minus z squared f of z squared is equal to 0. So it's a kind of linear difference equation. So it's a bit like differential equation, but instead of derivative, we have another action, which is given by the map, in that case, z gives to z3. And here we have a inhomogeneous order 1 equation, linear equation associated with this operator. And this is not specific to this special sequence. So behind this, there is a general result. So I give you a definition. If Q is a natural number at least equal to 2, then the power series, say with algebraic coefficients, is said to be a Q-Mahler function if there exists some polynomials P0 up to Pm which are not all 0, such that P0z Fz plus P1 of z f of z to the q plus Pm of z f to the q to the m is equal to 0, right? So we have a linear equation with polynomial coefficients, and here has a different the function where we iterated this kind of map, z give to zq, okay? And Alan Cobham, already in 1968, he proved that if an is q automatic, so here the q means the input base, then the generating series, sum of en z to the n, is a Q-Mahler function. Okay? But the converse is not true, so there are much more Q-Mahler functions than Q automatic series. So, yeah, what should I say about this Mahler function? So first, yeah, I'm writing from right to left. It's a bit disturbing, but to keep this. Right. So the first thing we have to do is, so remarks. There are very nice functions like log z or log z over log 3, which are not Mahler function. I say that because they satisfy a equation like this, but of course they are not formal power series. So the Mahler's method, which is a theory where the main goal is to prove to study the algebraic relation between Mahler functions at algebraic points, cannot be applied to these nice functions like log z or log z, okay, because they are not power series around 0. They are not analytic at the origin. So this is an important assumption here. One thing I didn't say is that here you have an inhomogeneous equation, but it's really easy to start from this and provide a homogeneous equation by just easy manipulation. So that I could add inhomogeneous terms in the definition. It doesn't change anything. So what we have also is that Mahler function, so they are meromorphic in the open unit disk, and if they are not rational, so meaning not a rational function, so the unit circle is a natural boundary. So you cannot extend this function analytically outside the open unit disk, and inside they are meromorphic, so singularities are at most poles. That's it. So now what we have is this Mahler function. They provide a more general framework. So because, for instance, these automatic numbers, so it just given Mahler function f at the point 1/2. So using Mahler functions at algebraic points, we recover by the remark of Coban. So we recover all the automatic numbers and actually much more. And so the conjecture I gave, so for instance, conjecture 2 and conjecture 3 I erase, can be generalized in this framework. Okay? So the main conjecture we have here is the following one. So if you can see it. So I pick natural number at least equal to 1, and for every I between 1 and R, let Fi of Z there is similar, here I restrict myself to rational coefficients, but there are similar conjecture when the coefficients are algebraic, but for some reason it's easier to state here in that way. So Fi is a Qi Mahler function. So we pick F1, F2, Fr Mahler functions with rational coefficients. And for every I, we let alpha I in the open unit disk be a rational number. And we just ask Fi of Z is well defined at alpha I, so because alpha I may be a pole of the function, so we want to avoid this. And the conclusion is that then if Fe of alpha is not rational for all I, then F1 of alpha, Fr of alpha are algebraically independent over Q bar. Okay. And no, I miss. Oh, well. So here we have F1 of alpha 1, Fr of alpha R. We have R different numbers, and again, the assumption is that these numbers are multiplicatively independent. Okay, so it means that maybe even the functions are related to different operators, not always the same. So it's Qi, Z give to Z Qi. So you don't know that much about this function. So you just have any of them. You take any rational numbers and just ask that the functions are well defined. And if the number is not rational numbers, so automatically all these numbers should be in particular transcendental and then algebraically independent altogether. So it's quite a strong statement about numbers. No, it's just natural numbers at least equal to 2. There is no restriction. And the only case this conjecture has been proved so far is when R is equal to 1. Excuse me? So the point should be multiplicatively independent. The QI, you are free. Because what we want to say is that if you have you pick several automatic numbers, okay? So in different bases. So the bases are related to the point. So the bases may be really different. But maybe you are 2 automatic in base 2 and also 2 automatic in base 3. You don't know the input base, you don't want the input base to come into the picture. So you want to be free on the input base, but then you ask that the output base are really different. Okay? And so it's just proved so far for R is equal to 1. It's resolved by myself and Colin Faverjon using work of Patrice Philippon again. So when R is equal to 1, it's a bit different because you only have one number. And what you say is that you pick a Mahler function with rational coefficient, and you assume it's well defined at a rational point. Then either it is rational or it is algebraically independent alone, which means it is transcendental. So you have this dichotomy between rational and transcendental. And this one has been proved, and in particular it implies the fact that square root of 2 cannot be generated by a finite automaton. So this is a result I proved before with Jan. Okay. Now, maybe, I don't know exactly when I started. You don't know? Okay. So now I want to explain a bit what Mahler's method is and what it can do for you. No, it's what is known is that it is only known that algebraic irrational, like square root of 2, are not automatic. Yeah, none of them, they are not automatic in all bases, and it's open, whatever the base is, it's open for all the other numbers. And maybe maybe the most easy should be E, and then either log 2 or pi, maybe log 2 and pi, and zeta of 3 should be maybe the hardest, but you never know. Yeah. I'm going to explain, but it's one special case is exactly this: taking a Mahler function with a rational coefficient, take a rational point, so the values is either rational or transcendental, and this cover this particular result, but by a different approach. So using Mahler's method, while with Jan Bugeaud we use the subspace theorem. So, and both approaches have their advantages and deficiency, which are not the same. So, what is Mahler method about? So, it's something which was initiated by Mahler, and one aim is to say something about the relation between Mahler function at algebraic point, algebraic relation. And when we want to study Mahler method, so we replace first the equation by linear systems, as we do usually with a differential equation. So we consider a system like this. So we have several functions f1, fm of z, which are related by some functional equation like this: f1 of z to the q f of z to the q, and this matrix is a matrix with rational coefficients, invertible matrix with rational coefficient. Of course, if you start with one Mahler function, so it satisfies one linear equation, you can use a companion matrix to move it to a system. And the converse is true, that if you have a system like this, each coordinates are Mahler function. Of course, if you assume that they are power series. So in our example here, maybe I can write down the system. So using the equation, so you easily get that 1fz. So we have a kind of very easy system, 1f of z3 and 1 plus z minus z2, right? Just a rewriting of this equation. So now we have a linear system with the function 1 and f. And what is important when you study such system is the notion of singularity. Of the system. So the singularities are defined as a number which are always algebraic, such that you can find a natural number n, 0, such that alpha to the q to the n is a pole of az, so or of a minus 1z. So which means that by pole of matrix, I mean pole of one of the coefficients, because the coefficients here are rational function by assumption. So there are special points where strange things occur. So you have to remove them. And when you study a differential linear differential system like the theory of Siegel E functions, so you have exactly the same thing. The particularity here is that the set of singularities is not necessarily finite. Actually, it's not empty, it's usually infinite. But it looks like this. So the functions are defined on the open unit disk. And if you pick a compact inside, so the singularity will be finite inside this compact. So it's infinite, but the accumulation points are all on the unit circle. Okay, so it's almost finite, say. And the main theorem we have in this direction. So, for instance, yeah. Okay, maybe I stayed before the theorem. So it's quite a long story, but there are several results. For instance, one important by Kumiko Nishioka in the 90s. And then there is a refinement by Patrice Philippon in 2015. And even some complement by myself and Faverjean in 2017, and which give you the following results. So it's a general theorem about this system. So let alpha, let's call such a system, say, M. So let's pick an algebraic number in the open unit disk, which is regular with respect to M. So, of course, regular means none in the set of singularities. So if the point is regular, then you have the following statement. So if you have a polynomial in M variables such that P of F1 of alpha, Fm of alpha is equal to 0. So, which means you start with an algebraic relation between the values of the numbers F1 of alpha, Fm of alpha. So you pick just a regular point, and you evaluate all the function solution of your system at this point. If you have such an algebraic relation, then the theorems say that there exists another polynomial with one more variable, z, and I could add that we can choose if we want P to be homogeneous with respect to the variable x1, x2, and then in that case, Q will be also homogeneous in the variable xi. So such that the two following things occur. So the first is that Q of z, F1 of z, Fm of z is 0. So which means that you start with some relation, polynomial relation between the numbers. It provides you a relation between the functions. Okay? And moreover, if you specialize z equal to alpha in this polynomial, you get P. So this is a very strong statement in the sense that it told you that each time you have a polynomial relation, an algebraic relation between these values, there is a functional explanation for that. So it comes from a functional relation that you have specialized at this special point alpha. So in particular, imagine you know that there is no relation between the functions. So you prove that the functions are algebraically independent. So this polynomial cannot exist. So the values are algebraically independent. It's really strong. Here, in this example, it's easy to show that f is not rational. So 1 and f are linearly independent. So there is no relation, homogeneous relation of order 1 between the functions. So there is no relation, homogeneous relation of order 1 between 1f and f of alpha at all regular points, which means that this number has to be transcendental at all regular points. So, and of course, it's much more easier to deal with functions than with numbers. And this theorem makes a translation. What you know about function will translate for the values. Okay? But linear relation between the functions are quite easy to handle. But I have to say that if you choose a general system like this, and you told me how to prove that the functions are algebraically independent, it's not that easy. So there is a whole theory for that, which is a difference Galois theory. So you can attach to this equation some algebraic group, which is called the Galois group associated with the equation. And the dimension of this group as an algebraic group is equal to the transcendence degree of the function, of the solution. But it's not really easy to compute this group. So it's not really easy to say something about the algebraic relation between the function. But the linear relation are more easy to handle. Okay, and for instance, as a consequence of this theorem, so we prove with Faverjean, we prove that if f is Q Mahler and alpha is an algebraic number, there exists, for instance, an algorithm telling you whether f of alpha is algebraic or transcendental. So which means that at any, for any values, algebraic values where the function maybe is well defined, taking any Q-Mahler function, you can say whether the value is algebraic or not. Be careful, I say there exists an algorithm. It's not implemented, so it's more, what will really prove is that, say, this question is decidable or something like this. So you can do it in a finite amount of time, but maybe it's very long time if you are in a concrete situation. So there are some people who are trying to do it properly. And the point is, if you remember the main conjecture here, so this theorem is quite strong, but essentially it proves the case R equal 1 of this conjecture, but nothing behind this. And the problem is that, and this is quite natural in this kind of statement, so we also have similar statement in the case, some similar statement have been proved, for instance, by Ziegel, Szydlowski, and Bakers about differential system, linear differential systems. But all these kind of theorems, they are related to different functions evaluated at the same point. And here we have some Mahler functions, but evaluated at different points. And if you think about say the exponential functions, so you know the Lindemann-Weierstrass theorem about the algebraic independence of different values of the exponential functions. And one trick is, if you want to prove, say, the algebraic independence of E and E square root of 2, what you can do is to consider the function E of z and E of square root 2 of z, and find a linear differential system where you plug these two functions and evaluate at the point 1. So this is one way to prove the Lindemann-Weierstrass theorem. But the point is that if you want to do the same trick with Mahler functions, you cannot do it, because so imagine you have one Mahler function f of z. You want to, say, study f of 1/2 and f of 1/3, so even with the same function. So the natural trick would be to consider f of z and f of, we want 1/3, so f of 2/3 z, and to consider the two functions as a point 1/2. But as I said, a Mahler function has the unit circle as a natural boundary, and it's always meromorphic inside the open unit disk. So the function you get here, it has a natural boundary which is different. It's not the unit circle. So it can never be a Mahler function. So when you do this, you lose the equation. When you do this with the differential equation, you still have a similar equation. So here, we cannot use a classical trick. And this is where we have to imagine different things and to use the Mahler's method in several variables. I can explain this a bit. So the idea is the following one. So Mahler's method in several variables. So now we are considering function of several variables, and we want to have equations which are similar to those one, but for function with several variables. And this was already introduced by Mahler in his early papers. So the way we can do that is to consider a matrix, say a n by n matrix with natural numbers as coefficients. And it's naturally act on the variable z1, zn, not as usual, but we consider a multiplicative action like this. So you get z1, z1, 1. You take the product, zn, z1n, as first coordinate up to z1, tn1, zn, tnn. So now you have a matrix which can act on the variables multiplicatively, and you can consider a similar system like this: f1 of z, several variables, fm of z with some az, and then you have fn of t of z, fm of t of z. So it's really look as similar systems. So the idea is what we try to do with Colin-Favergent is to prove results like this for this more general, in this more general setting. But behind this, there are a lot of difficulties. So it's not at all the same strategy or the same tools which are used. I mean, there are common points, but there are real difference between this and that. So there are conditions on the matrix T. You have to put if you want to hop something, but I will not describe them. And there are also conditions on the point alpha 1, alpha n. If you want to apply and to study the algebraic relation between the function at some algebraic point, which now is in Qn, Q bar n. So you need some restriction, and the kind of restriction you get is essentially that the coordinates should have some multiplicative independence, right? But I don't want to describe this. I just want to give you an idea of what is going on. Maybe, yeah. Why, if you are able to provide a theory for that, you will be able to prove maybe this conjecture. I'm able to give a hint for that. So I call this magic trick. So, which I learned from a paper of von der Porten. So consider this system here, okay? And imagine we are interested by proving the algebraic independence of f1/2 and f1/3, right? So the idea of the trick is to consider the matrix T is just 3, 3, 0, 0. So it will just act z1, z2, give z1, 3, z2, 3. So, and the kind of condition we have on T are satisfied by such matrix. So, and set f1 of z1, z2 is just f of z1, where f is our function that comes from the example. And f2 of z1, z2 is f of z2, right? So now we get a new system, which is 1, f of z1, z2, f1 of z1, z2, f2 of z1, z2 is 1, 0, 0, z1 square, 1 minus z1 third. F1 is 1 minus z1 minus z1 square. and the same with Z2. I don't know if you can read it. Here is the line with Z1, and here is the same with Z2. 1 plus Z2 minus Z2 squared and 0. And here you get F2 what? Oh, yeah. Thank you. So you get this system. And so now imagine that we have a result like this at disposal. So take the point 1, 2, 1, 3, 1 half, 1 third. So get alpha is 1 half, 1 third. So the magic part is that because the two functions they are related to different variables, and each one is transcendental. So for free, they are algebraically independent over Q bar of Z1, Z2. So the point is that F1, Z1, or say F1 and F2 are algebraically independent over Q bar of Z1, Z2. And this is for free. So what you expect is that then F1 of 1 half, 1 third and F2 of 1, 2, 1 third are algebraically independent over Q bar, which is just saying that F of 1 half and F of 1 third are algebraically independent over Q bar, right? So, and the point, I'm going to finish here. So, just let's think a bit about that. So, here, why this could be possible to get that? In this trick, you have to be really careful. So, the really good point is that this is clear, and you will be always in such situation because the variables are really different. But imagine you use the same trick at the point beta is 1 half, 1 half. Then with the same trick, I'm going to prove that f of 1 half and f of 1 half are algebraically independent. So something is probably wrong. And the point is that when you start this theory here, as I say, there are conditions on the point for which this becomes possible. And the condition in this specific examples are exactly that the point are the coordinates are multiplicatively independent. So what we did with Favergent is to get results completely similar to what Philippon and also myself and Favergent and Nishoka have done in the one-dimensional setting to this more general setting. But so the restriction we have here and here are not a problem, for instance, to handle this main conjecture. The restriction we have is that we consider some systems which are called regular singular. So I do not have enough time to explain what they are, but they really correspond to what regular singular systems are in the field of differential equations. So they are a subclass. So it means this regular singular condition is a condition on the matrix AZ. What gauge transform you can use to make it a constant matrix. So it's quite a strong condition, but which is satisfied generically. It's satisfied by all order 1 inhomogeneous equation. So if I have a diagonal system, it's always satisfied. And for instance, if you just consider a general equation like, remember in the definition, we have this P0z f of z plus Pm of z f of z to the Qm is equal to 0. So imagine you have an equation like this. If P0, 0 times Pm 0 is non-zero, so you don't want to see a 0 here and here, then your function belongs to regular singular systems. And what we proved with Favergent is that if you pick Hare functions like this, and all are regular singular, so the main conjecture is true. So the fact that if you choose any numbers, any algebraic numbers, if each value is transcendental, then they will be all algebraically independent if the points are multiplicatively independent. So actually, it corresponds to quite a strong part of this main conjecture, but unfortunately, not, I have to say that, and I finish with this, not all automatic series are regular singular. If it was the case, we would solve the conjecture 2 and 3 I gave at the beginning of the talk. But most of automatic series seems to be regular singular, but not all at all. So at this point, we cannot solve conjecture 1 and conjecture 2 and 3. But maybe somebody will be able to remove this condition, and then in that case, you prove all the problems I mentioned, except problem 1. So I stop here. Thank you. Yeah, I'm cheating a little bit. So what is true is that in most examples, I know, but essentially the known examples are order 1 or order 2 equation usually, and all those who have a name. So I think only the Rudin-Shapiro is not regular singular. But Baum, Sweet, Cantor, tumors, and so on, they are regular singular. The thing is that if you look at inside all the equation, so it's clear that if you choose the polynomial at random, that this condition is generically satisfied. But on the other hand, you have to be careful because there are perhaps many equations for which there is no power series solution at all. So it's clearly generic inside everything, but now I'm thinking a bit about how to prove it's generic inside the equations that actually have a power series solution. So there are still a few things to understand. Yeah. Yeah.
So there are three distributions of AZ. For example, that is almost constant.
Yeah.
So in your theory, so AZ is general.
Yeah. So what was proved in the multidimensional case before, there is one result by Kubota, which is essentially when the matrix here is diagonal, and then the coefficient may be rational functions. And one result by Nishoka, Kumiko Nishoka, where the matrix is essentially constant. And what we did is we extend, so this regular singular covers these two cases, but it's much more general than this. For instance, just if the matrix is well defined at 0, it's already regular singular. So it's really much more general. And also, the kind of results we prove are not just equality of transcendence degree, but there are finer results, like any relation can be lived to a relation between the function. And also, we allow to have transformation matrix that mix. For instance, you can choose 2 and 3. So a 2 Mahler function and a 3 Mahler function. And this was not possible in the previous results.
In your theory, you use a different theory of the power or something to improve the
No, the main thing, so we rework on the work of Loxton and van der Poorten. So in the 80s, they claim a thing for general matrix when they are well defined at 0, which is a particular case of regular singular, but their proofs was not complete, and then Nishioka and others proved smaller results in this direction. So we restart from this Loxton and van der Poorten ideas and fill the gap, and also to work with different transformation like 2 and 3. Inside the proof, you need some vanishing theorem, and we proved a more general vanishing theorem for which the main tool is the subspace theorem. And so it's really based on some work of Corvaya and Zanier, who prove general results in this direction, a general vanishing theorem. So, and there are other new ingredients, but no new theory, I say. New kind of results. We were influenced by what was recently proved in the case of one variables and in the theory of E functions. But there are many technical difficulties, and the new ingredient is essentially to fill this gap of Loxton and van der Poorten and to have this new vanishing theorem. Thank you.